It's great to be here. Thank you for having me this early in the morning. When I saw the time when I was supposed to speak and realized this is the time I only vaguely heard of, but yet here we are. So I'm going to talk to you about Wright's principle, which I want to be more of a thing. And we'll get to what it is and why it should indeed be a guiding light for the hardware security. But before we do, today is actually the Hobbit Day, if you didn't know. This is the day Frodo and Bilbo Baggins had their birthday. And of course, you know, my best impression of a hobbit, right? What do we want for our birthday, my precious? And of course, it's the ring of raw injection, right? Or, and you know, maybe the ring of power is not the best metaphor here, but perhaps the three elven rings are. So we want the ring to control the state, we want the ring to control the phi, and the ring to control the frames. And of course, as it turned out, there was another layer that was overlooked by the original designers, as it often happens in hardware security, and that happened to be the ring of power. But here is what Joshua Wright said during his presentation when he introduced the Killer Bee, the ZigBee security suite auditing tool. Security does not improve until practical tools for exploration of the attack surface are made available. And when I heard that, I said, this has to be a thing. It even made Wikipedia until somebody of the Wikipedian deletionist crowd took their eraser to it. And, but this is literally true, and we're going to go through my favorite examples of how this is literally true. I propose an extension of this principle, and this extension is a bus or component, or a phi, that does not come with tools for practical injection of both crafted inputs and states should be considered insecure. The longer it misses such tools, the more it's built up, the more insecure it should be considered. So when you're given a phi or a bus as a part of your bailiwick of security responsibility, these are the three CYA questions, right? Can you, well, CYS, can you sniff? CYI, can you inject? CYC, can you craft the packets and the payloads? And if you're not a native speaker on the bus, then somebody else will be. And if you don't have that capability on the bus, you're ceding it, you're ceding that control to the attacker. So tools do make a difference. We're going to go through these examples one by one. But remember the internet of the ping of death in 1990s? Remember the time when you couldn't open your machine at a hacker convention without having it blue screen because of a wireless driver bug? Well, packet and packet is something that Travis Goodspeed and my students did. And wasn't it interesting that you could actually emit raw ZigBee packets without ever owning a radio? USB has become a thing. Again, we had something to contribute to that. The revelations that your disks were likely to run a Unix that could be backdoored on the firmware level. And so you just ask yourself, why weren't these things obvious until they became obvious and until they exploded? And the answer is the tools were not there. The tools for the practical exploration of the attack surface were not there. And people have built up trust schemes that turned out to be based on sand. So the first and the most important of one of those things was, of course, TCP/IP. The idea that the internet was this friendly environment where you had to be liberal about what you accepted, and everyone could be dependent to be conservative about what they sent. And of course, there would be no bad packets, right? And then suddenly a ping of death, just an overlong ping, or a packet with the same destination and source IP, or one of those things. And if you think this time is done or is over and done with, look up Darwin nuke, an IP options packet that, oh, look at that, crashed macOS Darwin of not so recent versions. So, but what made the difference? Why is it that Darwin nuke is a big deal and not just one of those pings of deaths from before? Well, raw sockets and the Berkeley packet filter were really the savior of the internets, because now you could hammer on those stacks, and then people wrote libraries that allowed them to craft packets with least labor. LibNet, libdnet, netfilter made it possible to filter them so nicely, steal them into user land, mangle it there. This is still the foundation of every testing tool for your new internet protocols. And of course, you had to write this in Python, because who wants to write C if you can write in a scripting language? And we beat down on the internets. Until the internets, the TCP IP stacks were reasonably secured, and the only thing that was crashable, that remained crashable, was SCADA. Now this is good news, right? SCADA systems are still in the 1990s state. They still are likely to have their respective pings of death. And how did that come about? Well, you couldn't beat up on them until recently, as you beat up on the regular TCP IP stacks. And unless people are given the means to beat up on those SCADA stacks, things will not be nice, because people out there are not necessarily nice to your SCADA system. Of course, you know, we're talking about $1 million pieces of equipment rather than $1,000 ones, but this has to happen. But raw sockets basically brought the internet, the TCP IP stacks, with compliance to the rights principle on the layer 2 and up. And that's why we have a reasonable set of state with TCP IP stacks. So, is that the case with most operating systems, with most other parts of the operating systems? TCP IP stacks have been improved. Did anything else? Not really. And I am going to throw out this intuition, because one of the prerogatives of the Keynote is that you get to say things and then maybe people will prove them true. It's not just that all layers have parsers. It's not just that parsers are crashable. We know that. What we'll know less of is that parsers have dialects. Parsers that do not necessarily need to crash to do bad things to your system. They just need to understand things differently between two different components of the system. This starts at the phi layer. And this has been an unexplored land. And it should not remain unexplored if we are to depend on those wireless communications for, or those other phi communications, or those other bus communications for things such as SCADA. That's one thing, that dialects are underappreciated. We only look for crashes. We don't look for misinterpretations or non-equivalent interpretations. Our fuzzers are machines for finding crashes, not double readings, not double meanings, not ambiguities. That's one thing. And then the other thing is that we build our operating systems in such a way that the upper layers trust the lower layers state to be valid. And they trust it to not change from under them. If you think about how your Unix is built, if you think about how your any major operating system is built, this is pretty much it. You build layers of abstractions. And each layer of abstraction trusts the lower layers that the state is what it was that the abstraction is wrapping. And that need not at all be the case. So let's talk through these two things. And I predict that these two things are going to be where interesting vulnerability action will occur in the next few years. So let's talk about dialects. You have this problem that you want to design a protocol. And you've got a couple of fields, and then you add a couple more, and there are just not enough fields, right? Think of Wi-Fi. Think of 802.11, right? How many fields in a beacon can you count? Oh, I mean, 20, 50. Did you count the proprietary information elements in the beacon? Well, okay, not enough fields. And parsing is magic. And of course, parsers can crash, but we know this. Something else really interesting is going on. When you have n fields with m values each, that's an exponential growth that you've got there. It's m to the n combinations of fields that you're looking at. Now, do all of them make sense? Does the firmware check all of them? Does the firmware check all of those m to the power n parts? If not, then your hardware, then your firmware has dialects in which it will interpret some things as true when they are not, and perhaps some things as valid when they are not, and perhaps some things as invalid when they might be valid. And so the 802.11 was a prime example of that. We only started seeing that, of course. Behold the glory of the 802.11 beacon, right? It can be as long as 200 bytes. It has multiple variable length fields. It has sub-languages for those fields, each with its own parser. And all of this used to happen in your driver or in your firmware. In your firmware with the original cards, because only firmware was fast enough to deal with the microseconds timings. And yeah, Prism 2 Orinoco was the first card to allow Wi-Fi injection. And it was not even, as far as I'm aware of, and it wasn't even that easy because it was heavily dependent on the firmware. The firmware would, even if you gave your card a raw buffer, it would corrupt it. Well, it would rewrite it. It would correct it. But of course, what you wanted to send was the crafted frame. And you had to actually erase it in the debug mode with writing back the changes that you wanted to take place in the frame, and then half the time you won the race, and that's how you injected raw Wi-Fi frames. And then, of course, Atheros came along and shoving raw buffers out of your Wi-Fi interface got easier. And the way we knew this was this little talk called Hijacking a MacBook in 60 Seconds. You opened up, that's Black Hat 2006, you open up your MacBook, it starts pulling in your 802.11 beacons and probe responses, and boom, you have ring 0. A parser bug. It turned out that all those parsers were buggy, but the reason we found this out was that raw injection finally became available as a commodity. You could do that with your $100 card. You didn't need to have special equipment. And security just took a plunge and then got a lot better because tools for the practical exploration of that attack surface became available. And then, if you want more history of this, the uninformed 6.2 has this wonderful article about setting up for the exploration of this attack surface. And I could not resist pasting the bugs of the month of kernel bugs, November 2006, that were discovered in Wi-Fi within 1 month. So those are parser bugs. But what about dialects? Well, let's look. So here is a byte full of flags. So you've got 256 2 to the 8th combinations. Are all those flag combinations valid? Surely not. I am not going to dwell too much on 8211, but you know, you've got 3 types and subtypes that you use, and flags such as, oh, this comes from the wired side, which cannot happen for a management frame or a control frame. So most of that space of the values of these flags is invalid. So here is an old exploration of ours, which lobbed random values, or exhaustive 256 values of those flags at various chipsets and drivers, and saw how many of those they responded to, how many of those they saw as valid, even though the combinations of flags were nonsensical. And you can sort of see the binary tree. Linksys would respond to just about any combination of flags. Yeah, we don't care. It looks like a valid probe to me. Here is your answer. Various other vendors were a bit more selective about what they responded, but they still responded to a whole bunch of nonsensical frames. And the same for our other test when this were authentication requests and responses. So you see, if you imagine this firmware as this collection of basic blocks, and your packet picking a path through them, it turns out that however you connect those little checks, and you will not have all of them, that makes your dialect. So what that means is that you can talk to a particular device, a particular make of a device, with everyone else not hearing, even though they're listening, even though you're way loud, even though there is no noise. It's just because this device believes that this nonsensical combination is actually valid, cannot possibly test all of them, and others just discard them. So, ZigBee. So ZigBee was supposed to be a simplify, and then it developed, and then it developed some more. And then it ended up being no simplify at all. And so our next exploration of this thing was, well, let's see if we can do to that what we could do to 8211. But with 8211, if you noticed, we were at layer 2. With this one, thanks to the miracle chip, the ChipCon 2420, we could be at layer 1. And of course, the layer 1 is not just a monolithic layer. It contains of many. It consists of many sublayers. This chip allowed us to control a single symbols that we sent on the air. And Travis and my students built this device, which is kind of like a good FET. Those of you are probably familiar with that, who have done this, are probably familiar with this architecture. There is an MSP430 processor in the middle. It plays the middleman between your FTDI chip that gives you serial over USB. This is how you get your Python-made packets into this thing. And then the chip connected over SPI just sends them out. The antenna part was actually the most tricky part, and this is where most of the time was spent. But look at this as a raw sockets for ZigBee, as a card, as an interface that would send any frame that you care to send. And we were looking for dialects, but of course we found the packet in packet first. For those of you who have somehow missed it, it turns out that since the modulation of the preamble and the starter frame delimiter is exactly the same as that of the payload, you can send a packet that contains the payload in the application layer that is a valid frame, and occasionally you will hear that valid frame as if it were transmitted in the raw. So just being able to control the application layer on an unencrypted network, encryption would throw a monkey wrench into this, you could have the transmission of a raw frame without an actual radio. That's interesting. And why could you do this? Well, because the actual starter frame delimiter would be lost to noise, and for all the card knew, this was the preamble, and this was the starter frame delimiter. And it happily received that frame. And if you're interested in that, we have a site called Demystify, spelled as phi, and there were a lot more tricks that came from that. But what about the dialects? It turned out that ZigBee has dialects on the phi layer. You vary the length of the preamble, half of your chips would not hear the packet. Others will hear them just fine. We tested 3 dominant vendors. You throw garbage between the preamble and the starter frame delimiter, same thing. So you can shout past your IDS if you pick your malformation of the preamble just right, and it will not hear. Now, can this be the case on other buses and other PHYs? Sure. Andrea Berisani found this in Ethernet. Of course, they had to build quite a device to inject raw packets. There were no ready-made parts as for our mode that we built for ZigBee. But are we seeing that sort of thing built for other buses? We're not. Are we seeing tools for finding divergences rather than crashes? I mean, think of it. Everyone has habituated themselves to fuzzing. But fuzzing is something that generally finds you a crash, a corruption. This is how it's evidenced. Does it find you divergences? And of course, your system may consist of several components, not one. If they disagree about what is being sent, what does it mean for the security of your system? I feel that this is seriously underexplored. So, this is the kind of a birthday present that we security hobbits are missing from hardware people. Let's talk about stage in the OS. So the OS is this layer cake. And who knows this layer cake best? Rootkit authors. Because they instrument it in the most reliable ways. And reliability is their game. A rootkit that crashes is a very crappy rootkit. If you start looking at this, one thing strikes you, is that the upper layer thinks it's the boss. The upper layer depends on the lower layers to stand still. And if you control the bus over which your USB hard drive sits, or your normal hard drive sits, that is an entirely falsified assumption right there. So What if your callback that is supposed to notify you of the change is not called? What then? What good is your abstraction? We're seeing those kinds of, let's pull the rug from the higher level of abstractions and the security schemes based on that in Tocto. So here is a fun paper by Colin Mullner and others at Wood 2012. It's called Read It Twice. It's a hack of a smart TV. The idea of that hack is, okay, here's a security scheme that doesn't allow you to load libraries, but it does allow you to load signed flash files. So if you actually stick a gum stick in there instead of the hard drive, and control what that thing gives the file system drivers, the file system driver will happily verify the file, and then you switch the file system on it. And then it happily loads the verified file. Now, you've slipped into a lower layer, and you made that lower layer run away from the higher layer. This is how OSs are designed. They are not designed to do anything else. They're not designed to question what comes from lower layers. Or you might say, this is just a Tocto. We know Toctos. So let's try to unpigeonhole what a Tocto is, right? This very name of the Tocto, I say, is highly misleading. Unless your CPU is somehow a magic atomic CPU, you always check before you use, right? You always separate the times of check and the time of use. You can't freeze the state. You can't freeze your entire system before that. So a Tocto is really the state can change without you knowing. And of course, you have all kinds of schemes to combat that. Trusted computing introduced a bunch, and it's just one of those. But how much OS code is written to explicitly distrust the lower layer? Very, very few. And so we find ourselves in a situation when a lying device can do absolutely anything to the rest of the system. So PS Groove was on PlayStation 3, the jailbreak was one example of that. You set up the system to expect one thing, you give it another, you create a vulnerable configuration, and then you exploit it. The most interesting part is that you create this vulnerable configuration yourself. And then, of course, this is the problem that people have encountered as early as 1960s, 1970s. James Morris Jr., when he wrote his fundamental paper on types, wrote that, the programmer could begin every operation with a well-formedness check, but then, there would be no program, no useful programming left. How many OSs are built around types? Types are the solution for this. Types were the thing that allowed you to be reasonably clear about what kind of a data structure you trusted. How many OSs are type safe? It is a hard problem. It is going to be a harder problem if we keep the buses unexplored. My favorite thing, weird machines. All the data is bytecode. If you can manipulate complex enough data structure, then you can probably get the parser for that data structure to do just about anything for you. And we've done it with ELF, we've done it with Dwarf, we've done it with x86 descriptor tables. Can we do that with device metadata? If you switch the device metadata from under the driver and change that metadata, what will happen? So we explored it for USB. we built this little raw injection device called the phase dancer. And again, it's very much like any other raw injection device. You depend on a magic chip. In this particular case, the magic chip was the MAX 3420 controller. And that thing basically can speak USB out to this USB jack called victim. And once you can do that electrically, then you just need to build up the payloads, and you do that in Python, and you show them from the host through the FTDI chip on the right, on the left, my other right. And that's easy enough, because of course a USB is nothing but a network. And it's got nothing but packets. And if you can write a web server, then you can write a USB disk. But the most interesting part about this is not triggering buffer overflows, even though there are plenty of buffer overflows. The most interesting thing is setting up the transaction to expect one thing, and then feeding it another. Does it need to be a memory corruption? Not necessarily. It could be a weird machine instead. So people had fun with this. And UMAP 2 will be released at this workshop, I understand. And I'm very much looking forward to this. And people have started looking at working at USB firewalls and at stealing USB packets from the kernel and rewriting them. We had one project like that ourselves. And then there was another academic paper at Usenix, which interestingly did not quote ours or the phase dancer. You know, maybe they use some other magic. But again, things are improving because tools for the practical exploration of the attack surface became available. Now, you might think that devices are simple. I went to a hardware security workshop where people thought that, well, hardware is simple enough. You can check it through. And I'm like, gosh, no. You don't understand what your disk is doing. Unless you actually see what your disk is asking, what your disk driver is asking of your disk in the blocks, I'll bet you anything that you will be surprised when you actually see that. How do you know that Windows is booting off of your drive? It reads the boot sector 9 times. It's just what it does for some reason. How do you know a piece of forensic software is imaging your drive? Well, it's not reading your boot sector 9 times. Instead, it reads every sector in every block in order. If you want to give it something other than what it's expecting, just look for this pattern. Travis wrote this piece of software for rickrolling forensics of an iPod, which just notices this pattern and returns a bunch of blocks with never give you up, never let you down. But this is a toy. It has to develop into something bigger. Because the fallacy that you understand what your disk is receiving in the way of commands from your driver. Just imagine this tight coupling between your controller, your driver, and your disk. Just how easy it is to topple it if you actually start injecting into this bus. This should be done. And of course, hard drives can be backdoored. And in fact, that backdoor can be woken up by a pattern of accesses by a remote attacker, through your web server, through your web application, through all the other defenses, because causing a particular pattern of reads of blocks is not that hard and not that noisy. And it's a reasonable channel. So we want to BPF and scapify all the buses. And we want to BPF and scapify all the pieces of the OS. If you see a coupling there, you have to be in on it. You have to be a native speaker on that bus. Otherwise, someone else will be. And otherwise, you will miss an explosion of vowels when that happens. And then you will come to Black Hat to learn that your infrastructure is, not yours anymore, maybe. So one project that we're looking at and that we hope to inspire others to join is raw sockets for SATA. We could call the device, we would call the tool Satan, except such a tool already exists. If you remember, it was one of the first Nmap-like scanners for the internets. And of course, you could rename it Santa if you objected. It came with a script for that. So disks are trusted. Disks are very special in our trust. Kernel logic, kernel coupling with those is very tight. The attack models on the OS code, when data change from under that code, have not been explored. And the right place, as always, to be is the PHY. And so we can follow that. Packet through the kernel. We can follow that USB packet these days. We can't follow that block. This has to change. And so I posit that if it ain't right, it ain't right. Security will not get better until we redo, until we change the way we look at the basic OS components. And finally, speaking of rings of power and evil overlords and things like that, I understand that all of this may actually become illegal in the near future, because these are specially created devices that could be controlled as a part of the controls on the so-called intrusion software. And if your organization has not yet gotten involved in Wassenaar negotiations, or rather renegotiations, it should be. Because how many lawyers can a security researcher carry to work to be safe? How many, at which point the basic tools of our trust will not be available to us anymore because we'll need to get an export license. And by the way, you need to get an export license to talk to a foreigner, because what you talk about is an export in many regimes. Maybe, not yours, but it certainly will be in theirs. So how much of this chilling on the devices that inject, that change the standard execution path of a device in order to introduce new instructions, external instructions. Did I just describe a debugger, a hypervisor, any kind of a virtual machine? Well, yes, I did. Yes, there is a carve-out in the regulation for those. Now you will have to prove that your security device, such as a phase dancer or a SATA, man in the middle, is a debugger. Good luck with that. So with that, and on that sort of the darkness is coming note, I will leave you. Thank you.
Thank you, Professor. When I decided to introduce the Hobbit Day in my introduction, I had no clue it's going to be part of your talk.
Well,
I've never been more proud of my research.
Yeah, you will notice there were no cat pictures. The Hobbit theme is more powerful, at least for today.
Thank you for that. Does anyone have any questions?
It will not solve everything you're posing here, but I know that there are at least researches going on actually doing a full separation of data and instruction sets, even on the hardware layer. Do you have anything to say about that?
Yes, in fact, I do, quite a bit. I mean, having a hardware architecture is nice. Isolation has been the most useful primitive that we've had to date. However, what is data and what is code? Right? Even the code that we think of as such for, say, x86 is just basically data for the microcode interpreter. Yeah? Now, the example with ELF that I glossed over, right? Your typical binary loading path, right, involves relocation. Your data, your relocation tables, guides the relocator. So what you think of as a table is actually code for a limited execution model, except it turns out it's not so limited. Same deal with any complex format. What you believe is tables describing some data structures, they actually describe behavior because they drive some code. Now, can this code be turned into a generic automaton to carry out more than its intended function? Most likely, yes. So it's not just separating data from code. It's making sure that this data conforms to the types that can induce only this much computation, and provably so. Say, if you have a finite automaton, then you can prove that as it consumes inputs, it switches only between the states that it is meant to be in, and not in any other. Proving this for something that's an equivalent of a Turing machine, or even a non-deterministic pushdown, is quite hard or impossible under the circumstances. So it's not just it's not just isolation. It has to be containing computing power. It has to be, I mean, and type theory could be one method. I know of one OS that is fully typed. Unfortunately, what it doesn't do is seek on streams, because that's a tough operation to type. It's called ethos. I can share the links offline. But I mean, this is a really good question. At which point does data become bytecode? And we need to build systems so that every layer could not be hijacked, could not have its computation run away with that bytecode, becoming an emergent and unexpected virtual machine. So probably a longer answer than. Any more questions? Well then, thank you so much.